Hello, everybody, and welcome to our, wow, it's the fifth class already, the fifth class of our 272 Summer On-Shape, or generally CAD class. My name is Phil Simonowski. Been on a lot of robotics teams. I've been an engineer for about 7 or 8 years now officially, and I generally use SolidWorks and On-Shape daily in my work and for play with robotics as well. And Emily is here with us as well. She's from 272. Emily, would you like to introduce yourself? You're muted.
Hi, I'm Emily. Sorry. Hi, I'm Emily. I just graduated from LC, and I've been a part of Team 272 for the past 5 years.
Perfect. Thank you, Emily. So today, thank you all for coming. Today, I'd like to go over specifics surrounding the designs of gearboxes a little bit. We're going to use a gearbox as a way to learn new on-shape ideas while also learning engineering principles at the same time. So I'm going to start out with a presentation actually today from Team 3005, which is the team that I've been using those presentations from. So I'm going to kind of switch up the order a little bit. But then the rest of the class is going to be primarily just a quick overview of how to do a few things. And then we're going to move into designing your own custom gearbox. We're going to start off very simple. We're going to do like a single stage reduction gearbox to begin. And then we can take that, and if we're happy with it, and we have the time and desire, we can make multi-stage gearboxes with that. I'm generally going to be using FRC components. So for those of you who are more familiar with FTC, just it's the same stuff. It's just a different size, really. So don't be too concerned. And then yes, we're going to go over layout sketches. Specifically, this time using gears, but layout sketches are used all over the place. And then we're going to work on generating more features, learning how to use different features, as well as we're going to start to move into assemblies and bringing parts that we've made, parts from standard components and parts from other libraries into an assembly to build them all together into one universal thing. And then we're going to learn how to move these parts in an assembly and make them together so that they kind of make sense or they move how you'd want them to move. So as I said, I'm going to start out with the presentation today. So this presentation is specifically for 2-stage gearbox designs, and that basically just means that there's 2 series of gear reductions. So maybe there's a small gear to a big gear and then another small gear to another big gear. So the reasons why you'd want to design a custom gearbox over just like buying something straight off the shelf are to lower the overall weight of your robot or other things that you're designing, to minimize the amount of space that your gearboxes take up, to increase the strength or the power that your specific system is outputting, or maybe the off-the-shelf gearboxes aren't quite strong enough or capable enough for what you want to do. And also to get a very specific gear ratio for things like your drivetrain, or maybe a shooter, or maybe an intake, things along those lines, things you can't just buy off the shelf to get a very specific gear ratio for. So the general process for designing a gearbox is you need to determine, what gear ratio you need. First of all, that's the most important. What the overall reduction from the motor to the output device, whether that's a wheel or whether that's an arm or whether that's a roller, whatever, what that reduction needs to be. And then after you find roughly the total reduction, you need to break it down into each stage, or if you need multiple stages. For example, it's fairly difficult to get a 100-to-1 reduction in just one stage. So you might need a 1-to-25 reduction and then a 1-to-4 reduction, or any combination thereof that eventually multiplies to 100. And then after you've determined the individual ratios, you need to choose the gears that you want to use, what pitch they are, what their bore is, like how you actually mount them, so on and so forth. And then you kind of go back and forth. This is an iterative process. It's not like you go through each one of these and then you're done designing your gearbox. You might build a gearbox with a certain gear tooth or gear ratios, and then you say, that doesn't work. It doesn't fit how I need it to fit, or it just doesn't look quite right. And then you iterate on that and you make a modification to it. And then after you do those things, you generally lay it out in CAD in the orientation that you want things, the position that you want things. And then you fully make the CAD model after you make the layout. And that's what we're going to hopefully get to today. So to specify what you need the output to be, this is just an example that we're going to use here to show you how this process works. So the specifications of this gearbox are a Neo 550, which is this motor right here, a plate and standoff design, and that's usually because it's a fairly easy thing to custom manufacture for teams. Just plates and standoffs rather than like crazy metal 3D printed parts or 4-axis CNC stuff like that. Just plates and standoff can do wonders for a gearbox. And then a 2-stage compound gear train, like you see here. This is a 2-stage gear train. And they're desiring a 1/2-inch hex shaft output. So these are specifications you define when you're starting to figure out what your gearbox is. So this is just telling you guys what they're going to use. But in the real world, you would define these individually yourself. Do you want to use a Neo, or do you want to use a Sim, or do you want to use a Falcon? Do you want to use plate and standoff design, or would you rather have something else? Does it need to be 2 stages, or can you do 1 stage, or maybe it wants to be 3 stages, so on and so forth. These are all design decisions that you make when you're making your robot. And the specifications that they're giving us for the whole thing is that they wanted an output speed, and that's free speed, so that means no load on the system, no resistance, of 750 RPM. And they want the first stage to be 32 diametrical pitch, which we talked about. That diametrical pitch basically defines the size of the teeth. There's a lot more to it than that, but for now we'll just think about it as the size of the teeth. So as the number goes up, the size of the teeth goes down. So 32 means that in 1 inch of the gear tooth, or for every inch of diameter of the gear, you have 32 total teeth. And then they want the second stage to be 20 DP gears. So those will have slightly bigger teeth. And that means if you have a 1-inch diametrical pitch gear, that is a 20-tooth gear because it has a diametrical pitch of 20. And if it's a 2-inch diametrical pitch gear, it has 40 teeth, so on and so forth. So to calculate the overall gear ratio, you look at the free speed of the motor. And the free speed of that specific motor is 11,000 RPM. So to calculate the overall ratio that you want, you take the output speed, which was that 750 RPM, and you divide it by the input speed, which was that 11,000 RPM, and they get 0.0682, which is a 1 to, I'll call it 15 gear ratio. So that means for every 15 revolutions of the motor, the output only rotates once. That's what that ratio means. So when you're using multi-stage gear ratios, you want to try to have roughly the same ratio on each stage. If you don't have the same ratio on each stage, you could have more force being applied onto one gear rather than another, and it's just overall more efficient to try to have the same ratio at each one. But you can do larger or smaller on either of them, but it's preferable to do a larger reduction on the first stage. So on the first input stage. And that's because that's the stage that will see the least amount of torque, and it will have the least amount of likelihood to break the teeth off the gear. So this is calculating, this is just telling you how much you want for each stage. So they're shooting for, this is the 1 to 14 number, and they're taking the square root. When you take something to the power of 1/2, you're taking the square root of it. So they're taking the square root of this number, and they determine that 0.2611 is about 1 to 3.8, or 1 to 4, just about 1 to 4 gear ratio. That means if they have 2 gear trains that are 1 to 3.83, that will make their total of 1 to 14.67 gear ratio. So this first ratio might be 4 to 1 or 1 to 4, and the next ratio might be 1 to 4, and then they have a total of 16 to 1 because gear ratios are multiplicative. So the pinion gear is known as the gear that is mounted directly to the motor shaft, to the output of the motor shaft. It's also generally called the driving gear. That's the gear that brings the energy, brings the rotation into the system. And typically those are 32 dp, but you can get them in different sizes and diametrical pitches. And there's a bunch of different suppliers that provide these. And they're just saying that they're going to use the 12-tooth one from Robotics. And I believe some of those come with the Neo 550 motors. Here's some math here. So they're trying to determine what their individual gear teeth are. So if they have 12 as an input gear, they said that their input gear was 12 back here, the 12-tooth one. They're determining their output gear by using this equation, which is the gear ratio of the stage equals the number of teeth in the input divided by the number of teeth in the output. They do a little bit of algebra to rearrange the equation. And they determine that you need a roughly 45.96 tooth gear to make that first almost 1 to 4 gear ratio. Now, you can't have a fraction of a tooth in a gear. You need to have a full number of teeth. So this is pretty close to 46, but there is no 46-tooth gear available from our common suppliers. So what they have listed here, and what you would do as a designer, is you would go and see what gear teeth are available, and you would just choose the one that's closest to your design or that would work best for your application. So this one, this here is showing that from Rev, they offer a 42-tooth and a 56-tooth gear, and that's using 5mm hex shaft, what the FTC teams use as shaft material. And then Vex, which is another supplying company, offers a 40-tooth gear and a 60-tooth gear using 3/8 inch hex shaft. And if you're curious, this design, it's an extrusion that looks like that is hex shaft. And so they're saying, but you as a designer would decide, okay, which one of those gear teeth would I like to use? What's going to best suit my application? They're kind of making that decision for you, saying we will use a 60-tooth 3/8 inch hex gear. Now they've determined their first gear ratio, their first overall gear ratio. So in this slide, they're recalculating based on what the first gear ratio is, what is needed for the second gear ratio to get to the final ratio. I'm not going to go through all of these, but essentially they're just determining how much is left to reduce the motor output by to get to the desired rotational speed. So this is where a few more design decisions come in. They are looking for a 3/8 inch hex bore, and it needs to be that 20 dp. And they're looking at different suppliers. There's a bunch of different suppliers that supply similar things, and the ones they have listed here all supply 20 DP gears. And they found one from Vex Robotics that is 14 teeth. That's actually a steel gear, so it's a little bit stronger than your standard aluminum gears. But this is a point in the process where, as a designer, you would go and search the different options that each of these suppliers has and determine what's best for the application, what's best for your application. So now they do the calculation for, well, if they use that 14-tooth gear, what gear ratio, what would the final gear be to get them to their final gear ratio? And they determined that a 41.07 tooth gear would get them exactly to the ratio that they want. But remember, we can't have a fraction of a gear. We can't have 0.07 of a tooth. And it doesn't look like there's any commonly available 41 tooth gears. It's kind of an odd number. So they see that there's 40 and 50 tooth available from Rev and from Vex. And they went with the 40 tooth Rev gear. And just keep in mind, these decisions upon which gear can be used, it could be due to what's in stock. It could be due to cost between different items. Sometimes there's different features of certain gears versus others, like some might be lighter than others, or they might have mounting holes where you could put a hub or other things onto. So all those things are good considerations when you're choosing a gear. And then they need to recalculate the actual gear reduction using the real gears that they've chosen. And they come out to a final gear reduction of 1 to 14.29, which is different than their original ideal gear ratio, but it's quite close. And that's really all you need to do when you're setting these up. So in summary, they've decided that they have a 12-tooth pinion gear on the first stage. It's attached to the Neo 550 shaft. They have a 60-tooth, 3/8-inch hex aluminum driven gear that will mate with the 12-tooth gear. And then on the second stage, they have a 14-tooth and a 40-tooth. But do notice that they have different bore diameters. One is a 3/8 hex, one is a 1/2-inch hex. And the next step of all this is to make a layout sketch to make sure that those gears will work together, and then to actually physically model the gearbox. And that's what we're going to do next. Does anybody have any questions about any of that? I know that's a lot of information. So please, if you have any questions, let me know. All right. Moving on then. So I'm going to jump here, and now I'm going to talk a little bit more about the specifics of drawing gears in CAD and using, like, actually drawing to design for gears. That presentation did a really good job of explaining the math behind selecting gears. Now I'm going to talk about actually how to draw them and how to make the right spacings between holes and everything. So in a previous presentation, I've mentioned that gears have a very, very specific center-to-center distance. And that center-to-center distance is defined by what's known as the pitch diameter. The pitch diameter are these dotted lines that you see here. They are not at the end of the teeth of the gear. They are not at the bottom of the teeth of the gear. They are somewhere in the middle. And the pitch line is the point in which the two gears actually physically contact each other. And when you take those pitch circles and you make them tangent to each other, and you define how many teeth are in this gear, and you define how many teeth are in this gear, that will help you determine the exact center-to-center distance that any set of gears need to be. And really, the only equation you need to know for this, you don't need to know the gear ratios to determine the center-to-center distances. You don't need to know any of that. You just need to know this one right here, which is the pitch diameter is equal to the diametrical pitch divided by the number of teeth. And generally in FRC, we use 20 DP gears, almost exclusively. There's a few instances in which we use 32, but most of the time we're going to use 20 DP. So this is a quick math example here. With a 20 DP gear, diametrical pitch gear, and if that gear has 15 teeth on it, that gear will be 3/4 of an inch in diametrical diameter. So the diameter of this circle, this dotted circle here, would be 3/4 of an inch on a 15-tooth 20 DP gear. And to sketch that, you make the pitch circles tangent. You define the position of the gears relative to each other, so like at what angle they are, or if they're horizontal or vertical to each other. And then you start sketching out the other features of the gear train, such as where it's going to be bolted together, where your spacers are going to be, how your bearings are going to go, where, like what size shaft, and if the shafts are going to run into each other, so on and so forth. I'm going to do one more slide here before we jump into actual CAD. And just to be clear here, we're not designing gears themselves. The design of gears themselves, as you can see in this picture here, and this isn't even the whole deal. If you want to really talk about gears, sit down for a day and ask Mr. Cross, John Cross, about gears, and he will talk your ears off about the different capabilities and different options and different features in gears. But this just shows you a little smattering of the different things that you need to consider when you're actually designing a gear. That's not what we're doing here. We're designing the gearbox itself. We're just selecting the gears and then using those gears in a gearbox. And what this allows for is very much a freedom of design and location of things. You could choose where you want your gears, and you can change your design so that you can have your gears wherever you need them or to get them out of the way of other things. It's also generally lighter than buying something like a planetary gear system that's built onto the end of like the Neo motors you can get the modular planetaries for. And in FRC, as I mentioned, we usually use 32 for smaller teeth, and 20 DP gears are like the most common gears. And they usually are driven by a hex shaft, either a 1/2 inch or 3/8, or a hub that bolts onto the gear, and you attach the hub to something else, like a wheel or something along those lines. All right, so we're going to, oh, one more thing. We're going to get MKCAD on everybody's Onshape. So if everybody could log into Onshape. And I'm going to walk us through getting MKCAD. MKCAD is that library that I've been talking about. It contains tons and tons and tons of parts so that we don't have to model them individually. And there is an app for MKCAD, which is going to allow you to import parts into your assemblies much more easily. And so if you're logged into Onshape, all you need to do is go to the App Store. It should be right on your basic page, on your home page here, kind of with all the files and everything. Just hit App Store. And all these different apps will come up. There's a lot of really cool stuff on here. But we're, for now, just going to type in MKCAD. All one word. Just like that. And this one should come up. All you have to do is click on it. And as long as you're logged into your Onshape account, you just got to hit subscribe. There should be, I'm already subscribed. So it just says free and cancel plan here for me. But right in this general vicinity, it should say subscribe. Now, when you do that, you're going to have a new option in your Onshape documents to help you import stuff from MKCAD. So is anybody struggling with this? I know I moved pretty fast, and maybe not everybody's even logged into Onshape just yet. So let me know where you're at. or if you're having trouble. If you need the link, I can copy the link into the chat as well. In fact, I'm going to do that if that's easier for people. All right, when you've downloaded, or sorry, when you've installed or subscribed to the MK-CAD document, I want you to either unmute and say done, or type in the chat that you've done it.
Done.
Perfect.
Done. Done.
Fantastic. All right. So we're going to go into Onshape. I'm going to go into that same document that I've been working with in this class. And that's the one that I just named my own personal name. I believe everybody should have one of these documents you've been messing around with. And if not, just create a new document real quick. We're going to basically start from scratch here. So we'll go from there. So for our custom gearbox, we're going to do it a little bit more simple. I pulled in this one really complicated one because that's what you can eventually work your way up to. But we're going to start with just, for now, it can be any number of stages that you want, but I suggest starting with a single stage gearbox. And they have to have some ratio to them. So it can't be just a 1-to-1. It needs to be a big gear and a small gear of some kind, with the small gear being the one that's driven by a motor. So we're going to use 1/2-inch hex shaft to drive the gears. We're going to use 20 DP gears, which are the standard ones that are used in FRC. We need to have some ratio between the two. I would like everybody to use 1/4 inch aluminum plate to make that, because that's a very common material to use and access and to machine. That our team has a capability to make. Our team and many other teams out there have the capability to make parts out of that 1/4 inch aluminum. And we're going to use a 2-inch center to center motor mounting hole pattern. And what do I mean by that? On these motors, I'll pull up. I think it's Neo. There we go. On all of these size motors, they have the same center to center hole pattern. So it's this right here. That's the hole pattern between the mounting holes, and that goes all the way around. So there's actually 4 holes on here. So you'll need to know that 2-inch distance. You may need to know that those are 1032 screws. We talked about screws and fasteners before, so that is the hole that you'll need at 2 inches in diameter. And then you'll also need this hub diameter. That's this spot that sticks up along the motor. This is a feature in motors that's designed to accurately locate the position of the motor, because in things like gears, you need to have very, very specific distance between the center. If your gears are too far apart, they have what's called backlash, and that's where your gears go like this. And that can cause issues where the inertia from one gear could actually rip off the teeth from another gear if they have too much backlash. And backlash prevents your system from being accurate. The more backlash you have, the less accurate your system will be. So you really want your gears like this. You want them to fully mesh and to be in contact at all times. And to do that, you need a specific, accurate center-to-center distance. And that little hub that exists on the motors, the little 3/4 inch diameter, just over 1/8 of an inch tall hub, allows you to very accurately locate the motor. So you're going to use all of these features, all of these numbers, to generate your own simple gearbox. And I'm going to help everybody. I'm going to start out with everybody creating the first layout sketch. So follow along with me, and then I'm going to let you kind of go along on your own. I'm going to make the first layout sketch, and then I'm going to just make my first plate. And then you guys can go and make your own. I'm starting a new sketch on the front plane. You can draw this on whichever plane you want. I just use the front plane because I like the front plane. I'm going to click the N key, N for normal, to go normal to the sketch. And I'm going to draw 2 circles. And I don't need a diameter on them just yet. And I'm going to make these 2 circles tangent to each other. And I can do that in a bunch of different ways. I can select the 2 circles and click tangent. I can select the 2 circles and click the T button. T for tangent. Or I can select the tangent constraint and then select both circles. All those ways are valid ways to constrain things. And that doesn't just work for tangent. That works for concentric and parallel and coincident and so on and so forth. You can do any one of those orderings. I generally do the select the geometry that you want to have a relationship, and then select the relationship that you want them to have. Now, I missed my first placement of my circle, so it's not actually on that origin. So I'm going to delete this vertical constraint. Click on the center of the circle, click on the origin, and then click coincident. And now that center circle is locked on the origin. I can't move it anywhere. It's fixed there. But I can still change the size of each of my gears, and I can still change the relative position of each of my gears to each other. All right, next, I'm going to first make these construction geometry, because we're not actually extruding those gears. We're just trying to figure out where the rest of our features are going to be, like holes for bearings, or holes for the bolts, or the motor cutouts, so on and so forth. So these are just going to tell us where the holes go. They're not going to tell us what the holes are. I'm going to go to Rev's website again and look for a Pinion Gear. They have a bunch of different pinions here. I don't know if they have them for. That's 550. Neo pinions. Here we go. So these are all the different Neo pinions that they have. So they have a 10 tooth, an 11 tooth, a 12 tooth, a 13 tooth, and a 14 tooth, all in 25 DP. I'm going to go with the 12. Just because maybe it's a common part that we already have. We already have a 12 tooth DP. Now, again, the equation is very, very simple. I'm going to start my diameter, which I clicked the dimension tool and then click the outside of the circle. Or you can use the D shortcut, and it'll automatically run the dimension feature. Or I can use, I think last time I talked with everybody, you can use that S key for shortcut, and you can add the dimension tool to your shortcut bar. There's multiple ways to do the same thing in CAD. So I'm going to dimension the circle. And remember, in Onshape specifically, and most other CAD programs, you can do math in these dimension definitions. You don't need to like pull out a calculator and calculate what these values are. You can just do the math in there, and the math will actually stay. So you can just change the values in the math, and the numbers will auto calculate for you. So I have a 12 tooth pinion, right? 12 divided by 20 dp. And that's the equation that we talked about before. So that gives me a pitch diameter of that gear of 0.6 of an inch. And now if I instead used the 14 DP gear, I can just come back in here and type in 1.4 instead, and it will automatically calculate it, and that goes to 0.7. But I'm going to stick with that 12 tooth. So I've got my 12 tooth gear pitch diameter here. And then I want to see what other gears they have that Rev has that we can use. So I'm going to look up 20 DP gears. And look at that. They have a whole list of their own 20 DP gears. And we're going to use a half-inch hex one for now. And it looks like they have everything from 80 tooth down to 18 tooth in half-inch hex. So let's use something in the middle. Let's use a 36 tooth half-inch hex gear. So I need to do the same math, 32 teeth divided by my diametrical pitch of 20. And that gives me the diametrical pitch, the pitch diameter of the 32 pitch gear. So now the center distance of our gear is determined. This distance right here. This is a fixed number. We can't change this anymore unless we change the different teeth that we're using. So this is a 32, this is a 12, and a 32 and a 12 come together to make a 1.1 inch center to center spacing. And that's the critical aspect of this. It really doesn't matter where your gears are relative to each other at first, just as long as you have that center to center spacing accurate. Okay? But we want to make a gear train that is fully defined. We don't want any of these blue lines here. So for now, I'm just going to make this larger gear straight vertical of this lower gear. And now we have our full gear train. We have the basic sketch of what our gear train is going to be and where the center points are.
How did you make it straight vertical like that?
Sorry, I used a shortcut for vertical, which is V.
Okay, thank you.
And I'll do that again just so that everybody can see. Good question, Leon. I selected the center point of the circle, and I selected the origin point, which is also the center point of our pinion gear, right? I selected both of them, and then I hit the letter V. V for vertical. And you could do that another way. You could select both of those points, and you can click the vertical button that's up here, and it does the same thing. Or you can click the vertical button first, and then select the 2 points. And all three of those combinations, all three of those orders end up with the same output, that you have a constraint between the center point of your two circles. Maybe instead I want to make them horizontal. All I have to do is find that constraint here, delete it, and then click the 2 again and click horizontal. So you can add and remove constraints however you like, and it's fairly important to know which constraints are where. And this is a very simple sketch right now, but as you get more and more complicated, your constraints are also going to get more and more complicated. So start to get familiar with them and how they work and where to use them and when not to use certain constraints. So I'll do this horizontal gear train. That's perfect. Now, if I wanted to make a 2-stage gear train, let's say it has the same ratios, I would draw another set of circles just like this. And let's say if they have the same ratios, I can just make these two equal to each other. And I did the same thing as I did with the vertical constraint. I just used the E key for equals. I just clicked one circle, clicked the other circle, and then hit E. I'm going to do the same thing here. One circle, other circle, E. And I would make them construction geometry as well, which the shortcut for that is Q. Or you can click this button up here. So this would be a two-stage gear reduction where I have the 12 to 32 and then another 12 to 32. So bonus question, what is the total? I'm going to do it myself because I actually haven't calculated it. What is the total gear reduction of this two-stage system? And remember, that's a 12-tooth gear, 12 divided by 20, and then a 32-tooth gear. What's the total gear reduction between the two? Anybody? Maybe let's start off. What's the gear reduction between the 12 and the 32 first? Should be 1, 2, something. So for every one rotation of the pinion gear, or sorry, for every one rotation of the driven gear, how much does the pinion gear rotate? How far has the pinion gear rotated? Anybody? Is everybody still calculating it, or are they lost? Are they confused?
I'm a little confused.
Okay. So gear ratios, we talked about this last meeting, so totally understand if you're confused. Gear ratios don't work just with gears. They work with sprockets. They work with belts. They work with wheels even. If you have a small wheel and a big wheel, that's technically a gear ratio between the two. So if you have a 10-tooth gear, just as an example, and you have a 20-tooth gear, so you have one gear that's twice as big as the other. It has twice as many teeth, right? What is the gear reduction between those two? In other words, if you rotate the big one once, how many times does the small one rotate?
2 to 1.
Good. Good. Exactly. 2 to 1. So what I'm asking for is the exact same for this set. It's just not an even number that you can do the math in your head necessarily. You have a 12-tooth gear and a 32-tooth gear. You're welcome to use like calculators. You're going to have calculators readily accessible to you in real life, so I feel like you should be able to do whatever calculations you want. It's more about knowing what calculations to do than knowing how to press the right, or knowing how to do the calculations in your head. All right, Vihan, what do you got?
Is it 2.6 repeating?
2.6 repeating to what?
1 rotation of gear. 32.
Good, exactly. So it's 2.666 to 1 is how you would describe that, right? So for every 2.6 rotations, or 2 2/3 rotations of this gear will only rotate once. Exactly right, Vihan. Good work. Now, how about the two of them together? The two, so this is a two-stage gear train. So this gear rotates exactly the same rate as this gear, right? They're like on top of each other. It's kind of like that picture that was in this presentation. Where was it? Where was it? This, how the gears are on top of each other, right? So this gear and this gear are moving together. So what's the total ratio of the system? And I believe last week we talked about how to calculate that. And I'll give you a hint, it's not additive. If you have one ratio and you have another ratio on top of each other driven through the same shaft like this, it's not additive. Any guesses?
would you divide it again with the gear ratio? Not the gear ratio. So you take 2.6 repeating and divide that by 32 again.
Close. You're kind of on the right track. I'll give you a hint. Remember, these are the same gear ratios, right? This is the same gear ratio as this. So if this was 2.66, this should be a higher number, right? Or in other words, a lower reduction. But Vihan, you're on the right track. So if you divide it by 30, if you divide 2.66 by 32, you're going to get a much smaller number, which isn't what the reduction is going to be. It should technically be a higher reduction. Anybody? Let me give another example, and maybe this will make more sense to you. Let me just make these even numbers, and maybe that'll make that easier. So I'm going to do that example that I did before. We're going to use a 10-tooth pinion just to do the math. 10 and 20. Right? We have a 10-tooth gear and a 20-tooth gear, and a 10-tooth gear and a 20-tooth gear. So let's work backwards, and let's just think about this logically. So if this 20-tooth gear here, and this is kind of like our output shaft, but if we rotate that one time, how many times does this smaller gear rotate? I'm going to pick on people. London.
Yes.
Did you hear the question?
Kind of.
Okay. This is a 20-tooth gear, right?
Mm-hmm.
This is a 10-tooth gear.
Mm-hmm.
If I rotate the 20-tooth gear one time around, like all the way around, so from here, like all the way around the clock, like I went from 12 o'clock to 12 o'clock again, right?
Okay.
A 20-tooth gear, how many times would the 10-tooth gear rotate?
Twice.
Good. Very good. It would rotate twice. So now this 10-tooth gear and this 20-tooth gear, these are attached, okay?
Okay.
So they rotate the same amount.
Mm-hmm.
So how many times has this gear rotated? And that's kind of a trick question.
One?
No.
No, because they're connected.
Because they're connected. Twice.
Twice?
Good. Very good. Very good. So now if this one has rotated, if this one rotates twice,
Mm-hmm.
how many times does this 10-tooth gear rotate?
What's that? Well, that's 10. That's twice? No.
Not quite. If this one's already rotating twice, and this one has yes, it would be 4 exactly, precisely. Thank you guys for raising your hands. I'm going to pick on you next. I'm going to do the same example, but this time with a 10-tooth gear and a 30-tooth gear instead of a 20-tooth gear. This math is going to get a little bit more difficult. Oops. All right, Addie, since I saw your hand up, I'm going to pick on you this time. Let's say our 30-tooth gear rotates once. How many times does our 10-tooth gear rotate?
3 times?
Yes, exactly. Now remember, our 10-tooth gear and this 30-tooth gear are attached. They rotate together, right?
So 3 times?
Good. So this one rotates 3 times as well. So how many times does this one rotate?
6 times?
Good. Excellent. So do you see the relationship between these gears? It's not additive, right?
Yeah.
It doesn't add together. What does it do?
double?
Not quite. Well, it doubles when they were 2. Right? Or actually, sorry. Was 60 right? This one rotates. No, sorry. This one rotates 3 times, right? 6 is not right. That was my bad. I told you that you were correct. But stay on the line with me, Addie, all right? So this one rotated 3 times, right?
Okay.
So if this one rotates 3 times, and this is a 10-tooth gear, and this is a 30-tooth gear, how many times is this one going to rotate? It's not 6. I'll give you a hint. I made that mistake.
Okay. Not sure. Maybe like 9? No.
Good. Yes. 9. So what made you think 9?
That was like, I knew it was a multiple of 3.
Good.
So I just went the next highest.
You used the right word. What was the word that you just used?
Multiple?
Multiple. So gear trains, I should say staged gears aren't additive. They're what? I'm going to pick on you one more time, Addie.
Multiple?
Good. The word for that is multiplicative. It's a weird word, but
Oh.
multiplicative.
I was looking for that word. I remember, I thought I was like thinking multiple. I forgot to see.
All good. All good. Excellent job, Addie. So it's multiplicative. So if this is a 3-to-1 ratio and this is a 3-to-1 ratio, the overall ratio is 3-to-1 times 3-to-1, which is 9-to-1. And if I did instead of a 30-tooth gear, if I did a 40-tooth gear, right? Oh, not 400. If I did a 40-tooth gear, we have a 4-to-1 and a 4-to-1. And what's that total ratio? I'm going to pick on, wait, I can't see everybody. I'm going to pick on Grace. What's that total ratio? A 4-to-1 and a 4-to-1.
Is it 8?
Not quite. We said it was multiplicative and not additive, right?
Yeah.
So is 4 times 4 8?
No, 16.
Good, very good. So you take each individual stage's gear ratio and you multiply them together. And this is only for these compound gears, okay? So stuff like this where you have the first reduction rotates at the same rate as the start of the second reduction. Okay? It doesn't work if it's just a bunch of gears in a row. That you just take the input gear and divide it by the output gear, and it doesn't matter what's in between. It has no bearing on what's in between. So maybe I'll draw that just for an example. So if you do this, and then this, and then this, let me do another one. This, and this. And this one's a 40-tooth gear. So we have a 10-tooth gear, right? And a 40-tooth gear. And there's a bunch of gears in between. Like this. They're not on top of each other like these. They're just in line with each other. They're all one gear train. These gears have no bearing on the gear ratio at all. These 3 gears, all the ones that are in blue, this one, this one, and this one. They have absolutely zero bearing on the gear ratio because they're not the input gear and they're not the output gear. These gears are known as idler gears. That's all they do. They just idle. They just rotate. So what would be this overall gear ratio? A 10-tooth and a 40-tooth. I'm going to pick on Emily.
I'm so sorry. Can you just say the question one more time?
Sure. What is the gear ratio between this gear and this gear. This one, the bigger one is a 40 and the smaller one is a 10.
Would it just be a 4-to-1?
Yep, exactly. Precisely. And do these gears in between matter at all
No.
to the gear ratio? Good. They have no bearing on the gear ratio. Excellent. All right. I'm going to delete these and I'm going to continue this so that you guys can start making your own gearboxes here. So I've created my general gear layout. And so I'm going to finish this sketch, and I'm just going to leave that sketch as it is for the layout. And maybe I'll rename it C2C layout for center to center. And now I'm going to make a new sketch on the front plane again that is going to have the hole to mount the motor, which is going to be 3/4 of an inch, right? We looked at that before, 3/4. And then it's also going to have the center line. It's also going to have the 2-inch center holes for the mounting of the Neo or Sim or Falcon or whatever motor. So these are 2 center points for holes that I'm going to make 2 inches apart. I'm going to leave this like this so that we can rotate this wherever we want, and we can look at what works best for us later in the design. And then a 1/2-inch hex shaft is going to go through here. And if I do a 2-stage one, another 1/2-inch hex shaft is going to go through here. But I don't just want to draw a 1/2-inch hole. That won't give us any room for a bearing. So let's go on to Rev and look at hex bearings. See if they have any 1/2-inch hex bearings. They might not have 1/2-inch hex ones. Let me see. That's rounded hex. All right, we're going to go to the Thrifty Bot then. It's another website that provides bearings and such. So here's a 1/2-inch hex bearing. So from flat to flat on either side is a 1/2 inch. And let's look. They have a 1.125 inch outside diameter, and that's the number that we're going to use to make the hole for where the bearing is going to fit. So I'm going to come back here and I'm going to draw here a 1.125 inch hole for the bearing. And if I am doing the 2-stage, I'll just do the 1-stage for now. And then the last thing that we need is a plate to hold it all. And the plate is probably going to be symmetric about that. So what I did there, just to let everybody know, I selected the top plane and then the upper part of this box and then the lower part of this box. And I use the symmetric constraint. And that now means my box will be centered around the top plane. And then let's say I want some dimension from the edge of the hole, maybe like 3/8 of an inch. And then some dimension from here, maybe 3/8 of an inch, maybe a 1/2 inch. And then maybe the same thing over here, 3/4 of an inch. I'm going to draw one more thing. I'm going to draw the outside diameter of the Neo motor so we could see where that ends up. And I still have the Neo drawing here somewhere. That is 2.36. Dimension 2.36. And that's where the outside of the Neo motor is. So, does everybody see kind of the shape that I'm making? And I'm just going to make this vertical for now. Maybe I'll make this a little bit taller. So if I just extrude this as it is, it's going to be a box or plate that has the hole for the motor and the hole for the bearing. Okay? Anybody have any questions? Does anybody see an issue with this design as it stands right now? I'll give you a hint. It has to do with this circle. And that's the outside of the Neo motor. Isabella.
If you want to put like a shaft where the other gear is, the motor's going to interfere with that.
Exactly. If we want to stick a shaft through this whole gearbox all the way through, well, right now that hex is centered right there and it runs into our motor. And that's a problem. So maybe this gear ratio won't work right here. So this, what I'm trying to get across is, this is where, as a designer, you will design yourself to a certain point and then realize, oh, that's not going to work. I've got to make a modification to this design. I've got to stop and rethink which parts I'm using, or reconfigure where things are mounted, so on and so forth. So, so Isabella, what do you think we should do in this scenario?
Probably pick a new gear.
Very good. Very, very good. So I agree with Isabella. I think picking a new gear is probably the easiest one. So right now we're using a 40-tooth gear. Maybe we go to a, I don't know, 60-tooth gear. And how does that look? Does that look better? I think that looks better. Perfect. Now the next thing that we need to do is put holes in here, both for mounting the gearbox, but also for mounting the motors. So where can I put holes? Where's a good place to put holes? And I'm actually going to do that in this same sketch here. So we're obviously going to have two holes right there. And I'm actually going to use the whole feature. I'll show you guys the whole feature in this. But where can I have my other two holes? Or do I need two other holes? What if I put one? What if I put one here? Like on either side of this. And maybe these are like 1/2 inch. Ooh, that's too big. Not 1.2, 1/2. And this is going to space out between the two plates. Anybody see any issues with that?
Could it be difficult for like if the gear's on top and you want to move the plate, like getting to the screws at all, or?
It certainly will be. It certainly will be. I was thinking even a more kind of simplistic issue. Not simplistic, but like basic issue. If I have my plate and I have my gear here, I'm trying to put standoffs between the one side, this plate, and the one that's on the other side of the gear, right? So to be clear, let me go back to our presentation here. How these gearboxes usually work is there's one plate, and then there's a spacer, and then there's another plate on the other side, and the shaft goes between the two. All right, so do we foresee any issue with where I currently have my standoffs? Remember, this is the gear right here. That's our second gear.
The standoff would go to the gear.
Exactly. That standoff is currently going through the gear. So the gear, it's just a mechanical interference situation. Like there's no way that the standoff can go through the gear like that. This gear has to rotate. It's not like you could just put a hole in the gear where the standoff's going to go. Then the gear's not going to rotate at all. Vihan, very, very good. And let me maybe demonstrate that for everybody. For those of you who are struggling to see it. I'm going to make a line from here to here. It's going to be vertical. It's going to be construction because I don't actually want to do things with it. And then I'm going to use the midpoint constraint. So I selected the line in the center of the circle, and I use midpoint. And now those circles are defined. And I'm going to use the hole feature, which is this guy right here. And I'm going to do a number 10 bolt. Remember in our motor design sheet, it said that it was a number 1032, right? So I'm going to use a number 10 clearance hole, which means that it's bigger than a number 10 bolt so that you could slide the bolt through. If I did a tapped hole, that means that it would be threaded. If I did a drill, that means it would be exactly on size. But I'm going to do a number 10 hole, and then all I need to do is select the points where I want those holes. So let's say there's one here, one here, one here, and one here. Boom. And I'm going to make a new assembly. And I'm going to show you guys how to insert stuff into an assembly. If you click Insert, these are all the different part studios that you have. And I guess I've been working in Part Studio 3. And I want to insert our gearbox plate in here. So I click that Part 1, which is our gearbox plate, and click Checkbox. And I'm going to fix this plate so that it can't move anywhere. And to do that, you right-click on the part and click Fix. Right there. So that just prevents in an assembly from us being able to move that part. We want it to stay where it is. And on the left, remember how we added that app for everybody? On the left, you should see that MKCAD inserter, I think. And we're going to come in here and we're going to add a Neo motor. Neo brushless motor. And all you need to do is click on the part and it should basically automatically insert it for you. And now this part isn't mated yet. It's still free floating. So let's mate the part. And I'm going to use a Fastened Mate because I don't want this motor to move at all relative to the plate. I want it to be fixed and attached to the plate. So I'm going to hit Fastened. And I'm going to hit this little colorful guy here. And I'm going to hit this edge here. And that's going to bring those two pieces together. And then I'm going to add a bearing. Next bearing. Let's see. I want a 1/2 inch hex, 1/8 of an inch OD flanged hex bearing. So we're going to take this guy and we're going to mate it from this bottom edge down to this edge. If I'm going too fast for everybody, that's okay. I'm just kind of quickly going through this to show you how you go about using parts and MKCAD a little bit. So I just mated that bearing in there. And next I'm going to do standoffs. S-T-A. I think this is a configurable one, and it only gives you options with 2-inch ranges. That's kind of dumb. And here's our standoff. And so I'm going to take that. Can I configure that any other way? Change configuration. Oh, that's annoying. That should be custom. Anyway, I could take that and I can make that from here to here. And I'm just going to do the one for now, just for reference. And then what did we say this was? This was a 60 tooth gear. So if I type in 60T, 60 tooth gear, 60 tooth, 20 DP aluminum hex bore gear. That's what we want. So I'm going to click that part. Here's a gear. And then I also want, I think I did the 10 tooth. 10 tooth. 20 DP steel sim pinion. There we go. And I can fasten this gear, or actually this should be a Revolute. So Revolute allows something to rotate, but it doesn't allow it to slide along the length of. So I can do a Revolute gear, a Revolute Mate between there and there that has a slight offset of maybe 0.125 of negative 0.125. Perfect. And then the same Revolute from here to here with a, oh, that's cylindrical. I want Revolute. Revolute of here to here. Oh, it did take my first click. There we go. And that's going to be an offset of negative 0.065. There, now we have the pinion mating with the gear. But do you see the thing that Vihan pointed out? Well, that's a problem. I don't think that gear is going to rotate if we have that spacer going through it. So do we have any suggestions on how to fix this? Anybody? I'm going to pick on people then. London. Do you have any suggestions on how to fix our gear interference issue here?
I mean, I was thinking.
Mhm.
I mean, like, can you just like turn it around so I can see the back of it? That would
Sure. Now there's going to be a bolt here.
Okay.
In fact, I'll show you that bolt. I'm going to go to insert standard content. Keep thinking, but I'm just going to insert the bolt. It's going to be a socket head screw. It's going to be a button head. It's going to be a 1032. It's going to be 1/2 inch long. Perfect. I just hit insert. There we go. We've got a bolt.
Well, I mean, it looks like it's supposed to be in the middle there.
Oh, this isn't the shaft. That's going to be something else entirely. I'll show you. I'm going to put in a hex shaft.
I'm not sure, to be honest.
Inch hex is going to be inches. All right, think about it a little bit. Where else can we potentially put this? Again, we can change this part. We can totally. This is the part that we're making. We have full and complete creative control of this part right here. Everything else are parts where we grab them from like the library or things that we would buy. But this specific part right here, we have total and utter complete freedom to design it how we like. So where do you think it should go? How should we modify things? Any thoughts? I think Vihan had his hand up first. What's up, Vihan?
You can make the plate bigger and then move the hole for the shaft.
Good, good. Where would you move it?
You would make the plate bigger, and then that plate would be bigger than the gear, like more wide. Wide, and then you would put it up the edge or something.
So, like over here?
Yeah.
Perfect. Does everybody see what Vihan's suggesting? So how I would go about that, we're going to go back to our part studio. And we're going to edit this sketch. And we need to delete this line now, because that's not going to define where this goes. And this can no longer be vertical. We can't have that be vertical of that. It needs to go further out. We need to come like way out here, to be clear, somewhere in this vicinity. So this needs to be closer to like 2 inches. Maybe that's too much. Maybe 1.5. Maybe 1.25. That might be all right. And let's put this tangent to here. There we go. All right. And now since we modeled it like that, our hole position's automatically adjusted. And now when we go back to our assembly, look, it's already automatically fixed for us. Vihan, good thinking. And now I can take this piece and I can do, there's a thing called a replicate. And so I chose the instance, and then I can choose the face to replicate on. And now I made the other 3 pieces for us. Cool. And then I could take this piece if I wanted to, if I wanted the same piece on either side. And make that maybe like this. Like so. Boom. And look at that. We've got our first little gearbox. Oh, maybe we need to put a bearing on the other side too. So in about what, less than 20 minutes here, everybody, we made a gearbox. And I know I have experience and I've done this before. But what I'm asking everybody else to do for the rest of the class here is to work on your own gearbox similar to this one. And I will be here helping you or answering questions as you like. Your plate doesn't need to be square. It doesn't need to be symmetric. It doesn't need to be a lot of different things. You could put a lightning pattern in there if you want, like to take out some of the material. But all I'm asking you to do as your task for today and moving forward into next class is to generate a assembly somewhat like this one, with either a single reduction, or you could do multiple reductions if you like. And make sure you're using the correct center to center distance on your gears. So you'll see in this one, I put it right in the right spot. If I do a section view there, these should be the right. Oh, I think the center to center distance on these 10-tooth gears is different. Let me see. Pinion. So they make some of these interesting gears where even though they're a 10-tooth gear, their pitch diameter is not 10, which is weird. So, where is it? So here's the, which one is this? This is the, this is the 10-tooth, I think. So the pitch diameter in this is actually 0.6. So I would come into my drawing, my center to center layout, and instead of 0.5, I would do 0.6. That's kind of a weird thing with these gears. They don't exactly conform to that equation. So even though it is a 10-tooth gear, it has a slightly further spacing. That's only for those pinion gears. So now it has the correct center to center spacing. And you can actually see how they mesh well. Right? Something like that. All right. So go and be catters and go and make your own gearbox that somewhat resembles this or doesn't. It could be totally unique and different. Does everybody have this MK CAD inserter guide over here? Like if you go into an assembly, do you see this MK on the right?
I have it.
You have it? All right, good. Good. That means that when you installed or when you subscribe to the app that it exists over there. Good stuff. All right, I'm going to let everybody work on this for a minute. I have to go to the bathroom real quick, and then I'll be right back. Help yourselves. If you have any questions, just unmute yourselves and ask the questions, and maybe somebody else in the class can help you. Go online and look up different product information from different places. Rev is probably my favorite place because their documentation is fantastic on this kind of stuff. Look at different suppliers, get familiar with their websites, get dimensions, maybe go online and look up like single stage gearbox and see if you can get any ideas or suggestions. Lots and lots of things. Use all the resources at your expense. All right, I'll be right back. All right, how's everybody doing? Any questions about the layout sketch or the whole diametrical pitch thing? You know, it's a bit confusing. Oh, did I draw my thing on the wrong place? No, I'm good. Absolutely. So by layout sketch, I mean a sketch that you use only to tell you where to place things.
Yes, yes, I understand.
All right. So for example, let's go through, you know, this bar like brings you back in time, right?
Oh, no.
See that?
I did not.
So I'm going to go back in history because I am a time traveler, as are you, because you are using CAD. I'm going to travel back in time to when I only created this first sketch.
Okay,
So-
there's like 2 circles. You see, I was following along, and then I got lost, and then I stopped following along so I could watch. Because, yeah.
You're all good, all good. Don't sweat it. That's what we're here for. So what this sketch is showing is it's showing one circle that represents one gear, right? And another circle that represents another gear.
Mm-hmm.
Got it?
Yes.
Okay.
And you made the 2 circles tangent, right?
Yep. And that's because, as drawn here, those are known as the pitch circles of the gears, right?
Okay.
So they only contact in that one point.
No. Okay.
Okay.
Okay. I think I understand that. part.
So in other words, imagine instead of gears that you just have 2 wheels,
Okay.
2 tires. All right. So they don't have any teeth on them. It's just a piece of rubber and a piece of rubber.
Okay.
What is the pitch diameter of those wheels? It's like the actual outside diameter of those wheels, right?
Mm-hmm.
Cool. That's all pitch diameter is. It's the diameter at which the teeth contact each other.
Okay.
Does that make sense? Now, 2
Yeah.
wheels, when they contact each other, they're just tangent, right? They can't be overlapping each other, and if they're too far apart from each other, they won't even touch. Kind of the same thing goes for gear teeth. The only difference with gear teeth is that they have a profile of a tooth so that they get more engagement. A gear will slip much less than 2 wheels contacting each other would, right?
Mm-hmm.
Good. Have you ever seen how Ferris wheels are driven?
Yes.
How are they driven?
Ferris wheel. Are you talking about like what it looks like, or like the actual machine that turns it on?
Like the actual thing that makes it rotate.
Oh,
The actual thing that makes Ferris wheel rotate.
isn't it like a big motor? Like it spins
Yep.
the Ferris wheel?
And what's attached to the motor?
The 2 plate? Well,
Sorry?
I know it's the motor that makes the whole thing spin.
Yes, but what's on the end of the motor that attaches it to the Ferris wheel?
I'm not really sure. I haven't paid that much attention to the Ferris wheel.
All right, well, I'm going to show you a picture. Does that look familiar?
Not really.
Okay. The next time you go on a Ferris wheel, I want you to look at how it's driven, okay?
Okay.
Does this look familiar at all? Or this?
Not really. I don't pay attention. I sit in the Ferris wheel and just look around at the circle.
All right. Well, I challenge you, wherever you go in life, not just Ferris wheels, but everything, you will gain a lot by thinking about how the thing works.
Mm.
You don't have to, and that might not be interesting to you, but just every time you walk into a new building, think about how the roof is being held up. Or every time you step into, or every time you go into a car, right? Think about, well, there's a whole motor and a drivetrain and a steering column and the gears that are driving this whole thing. It's amazing. It's an amazing piece of machinery. There's every piece of that was purposefully designed. So my challenge to everybody, especially amusement parks, are great for this because they usually have their mechanical components exposed like this. I want you to think about how things move and work and are driven. So again, here's a really good example. It's just a wheel contacting the surface. And that's a gear train. This is a gear train. It really is. It's no different than two gears meshing. It's one really giant gear, which is the Ferris wheel, and then one really small gear, which is the tire. That's all we're talking about. It's the same exact stuff. No different, no more or less complicated. So moving back to here, does it make sense why those circles are tangent now?
Yes, yes, it does.
All right, cool. So now the difference between a wheel and a gear is that a gear's diameter is very, very specific. It needs to be a very specific diameter. A wheel, you can make any diameter, right? You can just increase the size a little bit.
Yeah.
But with a gear, if you're using a specific size tooth, you need to increase the diameter by the size that will add one tooth. You can't have like a fraction of a tooth on a gear. Does that make sense?
Yes.
So that's why we use that equation, which is, did I do this wrong? Oh, I had this equation wrong. It should be number of teeth divided by the dp. My bad. All right, so that was backwards, but generally speaking, this equation tells you what that diameter is. That's all it does, and that's all you need to use it for. And it's very simple. And just remember that this dp number almost always is 20. And all that means is that if your pitch diameter is 20, right, then if your pitch diameter is 1 inch, then you have 20 teeth. If your pitch diameter is 2 inches, then you have 40 teeth. If your pitch diameter is 3 inches, then you have 60 teeth, so on and so forth. Does that make sense to a degree?
Yes.
All right. So in other words, the diameter of the gear is directly proportional to how many teeth it has. Make sense?
Okay. Yes.
Just like circumference, right? Like this is a parallel to circumference. It's a similar equation to circumference. It just doesn't have pi in it. It's just a number. So the diameter in which the gears mesh, which is known as the pitch diameter, is determined by the number of teeth and how big the teeth are, which is this dp, the diametrical pitch. That's just how big the teeth are. All right. So when you design your drivetrain, I want you to use a 12-tooth pinion. So what's the equation for that diametrical pitch, or that pitch diameter? 12 teeth.
That was the equation we were just talking about, right?
Yep,
It was
12
like
teeth.
the number of teeth divided by like whatever the other word is. Yeah.
Yeah, it's called diametric. Say it with me.
Diametric pitch.
Diametrical pitch.
Diametrical. Okay.
Yep. So how many teeth did I say your gear has?
Didn't you just say? Did you say 12 or 20?
I said 12.
Okay.
Okay, so you have 12 teeth.
Mm-hmm.
And what's the diametrical pitch that we're working with?
20.
20, good. So what is 12 divided by 20?
Am I supposed to be applying this to my circle?
Yes.
Okay.
You don't even need to know the math. Don't bring out a calculator. Just go into CAD and type in, make a circle and type in 12 divided by 20 and let it do the math for you.
Okay.
All right?
Okay. 12 divided by 20. Oh, okay. I did it. It's a 0.06.
0.06 or 0.6?
0.6. I don't know what the other zero is, but there's like a line.
that other 0, that is the symbol for diameter. Whenever you see that symbol, that means that it's a diameter and not a radius.
Oh, okay.
Makes sense? It's a circle with a line through it, right?
Mm-hmm.
Yep. That is a it's called symbology or geometric dimensioning and tolerancing. That is a specific symbol that tells you that that number there is defining a diameter. And if there was an R in front of there, it would be defining a radius instead.
I put the dimension on like my smaller circle, but I'm supposed to put it on the bigger one.
Put on the bigger one. Try a 36 tooth gear. So you're going to do the same equation.
So 36 divided by 20.
Exactly. That's how easy it is. That's exactly how easy it is. In
Okay,
fact,
that's 1.8.
that is correct.
Okay.
So that means the diametric or the pitch diameter of a 36 tooth 20 diametrical pitch gear is 1.8. 1.8 inches. All right. You got it? Cool. Now those two are tangent to each other, right?
Yes.
Cool. I want you to tell me what the center to center distance of those two gears are.
Center to center distance.
From the center of one to the center of the other. How far are they apart?
Okay, so like click on there. Okay. It says 1.2.
I believe that's correct, but let's do the math.
Where do I place it? Can I just like place it anywhere?
Like around?
Yeah.
Where do you want it to go? You can make it go up. You can make it go horizontal. You can put it on a 45-degree angle. You can put it on a 35-degree angle.
I'm just gonna make it go down.
All right, make it go down. Cool. And now if you hit the green checkbox, did you constrain it to go down?
I think so.
Is everything black?
No.
What's blue? Is it the big circle?
Yeah.
Okay, so you need to, even though you pulled it down, you need to actually constrain it to go down.
So I gotta put horizontal constraint on.
Vertical, if you want it to go down, it's vertical, right?
Yeah. Oh yeah.
So you want to click the vertical button or hit the letter V for vertical.
Mm-hmm.
And then you hit the origin.
See, this is where I'm having problems. Because like I got the 0.6 and the 1.8. And then when I was finding the center diameter, it turned everything blue again. Just confusing.
I'm going to stop presenting. Could you share your screen? Is that all right?
Yes, I can. I think.
Because this is exactly what we're here for me to help walk you through this. Is anybody else having issues similar to London here?
I just need help figuring out like the sizes of the shafts and motor and stuff.
Got it. Okay. Cool.
Still
Sounds good.
Like it turned black, but then it went back to blue. I don't know what I'm doing wrong.
Okay. I know what you're doing wrong. Do you see how 1.2 is black?
Yeah.
I want you to delete 1.2, or actually just right click on it.
Okay.
So right click.
See, I don't have my mouse, so this is gonna be difficult.
You should be able to right click with your trackpad.
Maybe my right click button sucks. This is the right click for 1.2. Is the cursor supposed to look like this?
No, you have vertical selected. Click the escape button.
Oh.
There you go. Now right click on that.
Right click. It's supposed to turn brown, orange.
Now, did you right click?
Yeah, I did. My right. Yeah. What?
I think you're just regular clicking.
I may be. I don't.
Click escape. Click escape. Yeah.
Okay.
Try to right click.
See, my touchpad. I've had this laptop for a long time. It's kind of
all right. Try to get a mouse for next time. It's much easier to CAD with a mouse.
I'm gonna be at my uncle's house next time we do this. He has the mouse.
All right. Cool. Sounds good. So just delete that dimension from now. We'll be able to work with this. So just hit delete. Good.
Okay.
Do you want to center the small gear on the origin? I think you do.
So I would click this and this.
Yeah, you can move that one if you want. Like move the big circle out of the way.
I've been trying to.
Click and hold and then drag it somewhere. There you go.
Oh, I didn't know that. Okay. So you would click this and
Yep.
this, and then this.
Yep. And then click, nope, not vertical, but yeah, coincident. You got
it. Right?
Yep.
I did.
Perfect.
I was on black. Yeah.
Do you see how it turned black?
Yes.
That means that circle is now fully constrained. It can't move anywhere. It can't get bigger. It's smaller. It can't do any of that. Right?
Okay, that's cool.
You can't do anything with it.
Then I can like move around, right?
Yes. Yeah. So now you have to decide where you want that other gear.
Can I make it vertical?
Sure.
Up and down. Okay. You take this. No, wait. Now what do I do? Do I click V or do I have to click the?
You can click V, but then you have to click the other thing that you want it to be vertical too, which is what?
Yeah. I don't know what I did.
The origin. No, you were right.
This. Do I have to click this?
You could, yeah.
I could. Okay.
And then click vertical.
Oh,
there you go. Beautiful.
Okay. Okay.
Beautiful. All right. You've created your layout sketch. So I want you to click the green box now.
I did it. No,
right,
I just zoom out.
Yep. Now you're going to make a new sketch that's going to start the actual plate where the motor's mounted to, right?
Okay, so I got to make a new one. So if I sketch?
Yep.
Okay, and then it's the front plane, right?
Yep.
Okay.
There you go. All right, I'm going to let you go for a little bit more, London. You're doing great. You're doing great. Just keep on going the same route. Just remember that the motor has a 3/4 inch thing on it, and that for the bearing, you're going to need 1.125 size hole. Okay?
Okay.
So make a plate with those two features on it. All right. Vihan, what's up?
So I have a question about the shaft diameter.
Sure.
Yeah, diameter. What is the diameter of the shaft?
The shafts that are generally used in FRC are hex shafts. So they actually don't necessarily have a diameter, right?
Oh.
Like it's a hexagonal profile. But
so
they're
when I'm making the circle, what should I put as the, I guess, diameter?
For which hole? For the driving gear or the driven gear?
No. I'm saying for the shafts that like there's like a housing to it.
Yeah, it's called a bearing.
Oh, okay.
So I'm not sure if you were here during that one meeting. So what a bearing does is a bearing lowers the friction on rotating elements. It can do it on linear sliding elements as well, but generally on rotating things. Okay?
Yeah. So
we use roller bearings generally in FRC and in FTC. We use roller bearings there too. They're just much smaller. So that bearing that we're talking about, it has an outside diameter of 1.125. Okay?
Here, thank you.
Yep. All right, who's next, or who would like to share what they have so far? If not, I'm going to start just picking on people.
I'd have to ask questions.
Absolutely, yes.
I can't find the hex bearing.
Did you install the MK CAD app?
I did.
Do you have the MK in the assembly?
Mm-hmm. I found the motor. I just can't find the bearing. Well, I find lots of bearings. I can't find the hex one.
Might have to search like half an inch. If you just type in hex.
Hex.
And then there should be a drop down with bearings, like a menu option for bearings.
Yeah.
Do you see that?
Mm-hmm.
All right, cool. So in there you should see a 0.15 inch hex ID, 0.125 OD flanged bearing. See that?
Oh, yeah. Brilliant.
Click on that, and it should come to.
Oh, pretty.
There you go.
Mount it, but
All good. Mounting it's just the next step. Isabella, what's up?
So I think Vihan might have just asked this, but how big should we make the hole for our plates for like where the motor and the gear go?
So where the motor goes, let me share my screen and I'll show you. And this is actually, you know what? I'm gonna let you figure that out.
Okay.
The drawings for all those parts exist on the websites for the manufacturers. Okay.
Okay.
Or another option is you can insert the model into your assembly and then just measure it and then design your part based off the model.
All right. So
you will figure it out.
Sounds good. Thank you.
And that's how a lot of design is. It's like you'll design something so far and then you're like, well, I don't know what size to make this thing. Well, okay, then you go online, you find the model for it, and then you bring it into your assembly, and then you take measurements, and then you change the dimensions of your thing to fit to that part. That's how a whole heck of a lot of design happens. The same thing goes, like, not all of our parts will be able to find on MKCAD. Some of the parts we'll buy from McMaster. And McMaster has its own CAD library. We actually went and downloaded some parts from McMaster earlier in the class. And so that's a situation in which you'd go to McMaster, you'd download the CAD model, you'd import it into Onshape, and then you'd take measurements from that part to make the features that will interface with it. Maybe it's like a bolt hole pattern, or maybe it's a keyway that's specific to that part or something. But the questions that you're asking most of the time when you're designing something should be able to be answered by the parts that exist online somewhere. Does that help make sense?
Yes.
Cool. Vihan, what's up?
What type of motor should we be using?
Well, we have options. I know that 272 loves the Falcon motors. So if you just type in Falcon.
Thank you.
See Falcon? Just say Falcon 500 or simplified Falcon 500.
I'm searching. It's loading. Yeah, Falcon 500 motor.
Yep.
Yep, I see it.
So if you insert that.
Should I say no shaft, short shaft, long shaft?
I would say probably short shaft or the 8mm keyed one.
All right.
Either of those two. And I will explain what's going on with the shaft because it's a little bit confusing, okay?
I inserted it, but I cannot see where it inserted.
You can click on it and then right click and then click isolate.
Oh, it just popped up. Okay. Thank you.
Yes, yeah, sometimes it takes a minute for it to load. But so Vihan, so let me explain the shafts, okay? On these Falcon motors, they use something called a spline shaft. And I'm going to share my screen just so that in the recording that people know what I'm talking about. So they use this spline shaft. It's a shaft that almost looks like it's a gear tooth profile, right? Like it's got almost gear tooth looking shapes to it. But what this shaft is it's a way to transfer torque, a lot of torque in a very small diameter. Normally you have something called a keyway. So we talked about this in the one class. Normally you have something called a keyway that transfers torque, and a keyway is something like this. Let's see if I can get a bigger picture. There we go. So you have a notch in the shaft like this, and then you fit this key, which is just a little square piece of metal. And then you have a similar notch cut out in the hole in the bore. Now this can transfer the torque between the shaft and the bore, but the problem is it's only one point of contact that transfers the torque. And what can actually happen is you can actually take that key, that little square piece, and you can split it right down in half and shear it completely off if you have too much torque. So what a spline shaft does is instead of one single point of contact, you have like a however many teeth are in the spline point of contact, and it's generally a much more robust way to transfer torque. The issue is that it's a lot more difficult of a part to make compared to a key, and it's also like it's more difficult to tolerance, and you need to have a part that mates with it that has that same spline profile in it. So like with this shaft, you could only put pieces on here that fit this specific profile, which isn't always what you want. Maybe you want to be a little bit more flexible. So for this one, you're going to need a spline shaft pinion. So if you look up spline in MKCAD, do you see on my side here? See how I typed spline, right?
Yep.
So when you type spline, the gears that have splines on them should show up here. And those are, let me look up pinion actually. So when you see the falcon pinion, that means that it's the spline shaft. And that's, I only know this because I've been doing this stuff, so I understand if you're confused. And this is FRC versus FTC. So this is a new like parts to you, so no worries. But anything that you see the falcon shaft, that means that it has the spline on it. And I'll insert this one. This is an 11-tooth spline. And it just came in right there. You can see that it has that same spline profile in it. See that?
Yep.
And that's what I mean by that mating profile. So I can go and mate this surface and this surface, and you'll see that those splines match up perfectly.
Yeah, for some reason when I loaded in the motor, the shaft of the motor is just like a square.
A square?
Do you have to share my screen?
Yeah, please. Oh, look at that. I think that just means that the part's still loading. That's weird.
Yeah.
Yeah, usually when you see that, that means that the part's still loading. What CAD does, what a lot of CAD programs do, is they'll simplify the model a bunch when they're loading so that it'll load faster.
Yeah.
So can you go back into MKCAD on the right there?
Sure.
And there should be if you type in Falcon again, there should be a simplified version of the Falcon that might load a little bit quicker for you. And it's the same thing. It just doesn't have all the bits and bobs that the regular Falcon does. I want to see if it works. This didn't work for me just now. Yeah, it's not working for me at the moment. I don't know why, but oh, it looks like it did work for you. It'll load. Your computer's just slowing down. In fact, if you delete the other Falcon, that one will load faster. So if you delete the complicated one. Click on the top level. You're clicking on the part of the sub-assembly. Does that make sense?
Where?
So do you see right below Origin, it says Falcon 500?
Yeah.
Delete that. Don't delete the part inside of it.
Yeah.
And now you have two things selected, so you have to unselect that one. Yeah, now you should be able to delete it. There it is. All the way at the bottom.
Okay.
Perfect. So it looks like just a block. That is a simplified version of the Falcon 500. I'm not sure why it's not loading. You could try to refresh your screen.
I'll do that.
Refresh that. All right. How's everybody else doing? How is Grace? How is Isabella? How is London? Grace, can you are you having any issues?
I'm trying to use the like the CAD extension, the MK CAD, and it's not really loading for me.
Yeah, sometimes it's very slow. I'm going to share my screen for a second. I'm going to kick Vihan off. Okay, he already kicked himself off. Good. There's another way to insert parts besides using the MKCAD thing. And that's just straight through this insert. So what you have to do is you go insert, other documents, public, and then if you just search up MKCAD, it'll show up with everything. Gearboxes, pulleys. Don't use any of the ones that say copy. Do not touch any of the ones that say copy. All right. So we want to go to MKCAD-motors, for example. And inside of MKCAD-motors, they have the Falcon motor, which is the same one that we just have right here. Oh, make sure you go into assemblies too. I just inserted all the parts. Not the, you don't want to insert the parts. You want to insert the assembly. Does that help?
Yeah.
All right, sweet. Because that works a little bit quicker. This app is still in development, and it is a little bit slow at times, especially like if you let your computer open or if you insert every one of these parts into one of your documents, it'll start to load faster. But that's a pain, so don't do that. All right. All right. Well, it's 9:05. Does anybody have any questions before we head out?
Oh, I do. Will we be like working on this again next time? Because I'm definitely not done.
Yes, we will be continuing working on this next time. We're primarily done like the teaching of like the basics of CAD, and we're going to start to just use more and more of the things we've learned moving forward. I'll still be doing a presentation, like an engineering presentation of some kind each time, but we're going to focus the rest of our efforts on actual time in CAD, making things, building things, learning about different ways to model things from here forward. All right.
Sounds good.
Perfect.
Thank you, Phyllis. It's fantastic. I'm learning a lot.
All right. Good. Thank you very much. I appreciate the validation. All right. I'm going to stop the recording and thank you all for coming, and we will see you all next Monday. Bye now.
Bye-bye.
Bye.